So our next speaker is Gerard Pelegri from the University Autonoma of Barcelona. He's working on his PhD with Veronica Finger and Jordi Montpart. And the title of his talk is there, so I don't have to repeat it.
Okay, so good morning, everyone. First, let me start by thanking the organizers for giving me the chance to be here in this very wonderful meeting.
I have to tamper with this.
Okay. So, as I was saying, let me start by thanking the organizers for giving me the chance to be here and to present in this very wonderful workshop the work that we have been recently doing in the Universitat Autonoma de Barcelona with Jordi Montpart and Veronica Finger, who are here in the audience, and also in very close collaboration with Anselmo Marques and Ricardo Diaz from the University of Aveiro in Portugal, and with Andrew Daly in the University of Strathclyde in Glasgow. So this is the outline of my presentation. I will start with a brief introduction, basically about the importance of complex couplings for quantum simulation in recent years, and then I will move on to discuss the specific system that we have been studying recently in this work, which consists of a gas of ultracold bosons loaded in a diamond chain and occupying the local states of orbital angular momentum. So I will first discuss the physical system and explain why we obtain complex couplings in this particular configuration. And then I will discuss two particularly interesting physical limits. The first one will be the single particle limit, in which I will show that because of the presence of orbital angular momentum, there are gap openings and topological edge states appear. And then I will also discuss the limit of strong interactions at unit filling, which, if you want, is the Motin-Sullivan limit, in which I will show that the system can be used as a quantum simulator of the XYZ Heisenberg model of magnetism. And finally, I will start by drawing some conclusions. So as I was saying, and it has been commented in very wonderful talks along this workshop, in recent years, the possibility to engineer complex couplings in systems of ultracold atoms has become of great importance for quantum simulation purposes because it allows to simulate gauge fields and other effects. So to cite only a few examples, some of them have been discussed here. There are many other examples of implementation of complex couplings. Relevant models of physics, such as the Hofstadter model, XY spin model, or the Haldane models, have been simulated with ultracold atoms, and also using the synthetic dimension approach that was developed at the group of Maciek Levenstein in ICFO. So for example, in Florence, as Leonardo Falani very wonderfully explained, they observe chiral edge currents with fermions, and also it has been observed with bosons. So typically, the techniques that are used to obtain complex couplings and thus artificial gauge fields are either the combination of radio frequency and optical Raman coupling fields. Also, the shaking of the optical lattice has been used. And here, I would like to discuss a different approach to obtaining complex tunneling amplitudes, which is using the complex couplings that appear naturally in systems of ultracold atoms carrying orbital angular momentum because of the geometrical configuration. So the specific system that I will be discussing in this talk is this diamond chain. It can be understood as an infinite repetition along one dimension of this unit cell here, in which there is a central site coupled to two other sites forming 90 degrees angle, and also coupled to the next cell. And since we are considering that the ultracold bosons can occupy the states of L=1 orbital angular momentum, the total bosonic field operator will take into account the possibility to create either plus or minus states in each of the sides of this diamond chain. So before discussing the Hamiltonian of this diamond chain, I would like first to discuss briefly what are the physics of of states with orbital angular momentum inside the couple potentials. So the simplest case that one can consider is just two cylindrically symmetric traps which support this kind of orbital angular momentum states in which one always has the freedom to choose an arbitrary phase origin along the line or not that is uniting these two couple potentials. So in this system, there appear three different couplings. The first one would be the self-coupling, which is due to the breaking of cylindrical symmetry in global in this configuration. And then we have the two couplings that we would expect that are cross couplings involving and not involving exchange of angular momentum. And an important point that I would like to stress here is that the relative strength of all these three couplings depends on the separation between the traps. And this we will see that is important for what I will discuss next. So this is when we have two traps, but then complex couplings can appear when one considers more than one trap. In this case, if the traps are not in line, if one chooses the phase origin to be along one of the lines uniting the traps, then what will happen is that along the other line, the phase origin will not be zero, and complex couplings will arise for the tunneling amplitudes that involve exchange of angular momentum, which are the self-coupling and the cross-coupling with exchange of angular momentum. So since here we can observe that the coupling strength decays quite rapidly with the intertrap separation, if we consider the central angle in this triangle configuration to be larger, much larger than 60 degrees, we can consider these two traps to be uncoupled. And finally, the Hamiltonian describing the dynamics of the 6 states that can be occupied in this configuration is this one where you see that there appears a complex phase that depends on the central angle of the triangle. And a subtle point here is that the self-coupling at the central site has contributions both from the left and the right, and for a particular angle of 90 degrees, it vanishes. Okay, so after explaining this, I am able to introduce the total Hamiltonian for the diamond chain that I will discuss during the rest of my talk. As usual, if one considers the class of bosons in this diamond chain, the Hamiltonian can be decomposed into two parts, the interacting part and the free kinetic part. The interacting part has a form that is the usual form of a Bose-Haber model with interaction between states in the plus orbital angular momentum state and the minus orbital angular momentum state, and additionally, one term that takes into account the interaction between these two modes. And then the kinetic part of the Hamiltonian takes into account a term that does not involve exchange of angular momentum, and then another term that does involve exchange of angular momentum, and for which there are some complex phases along this line here, because we have chosen the origin of phases to be along this line. So these are the couplings that you can see acquire a phase in this model. Okay, so we will see that the appearance of these complex phases gives rise to interesting physics. So the first model in which I would like to discuss these effects is the single particle limit, in which the first thing that we can do is to compute the band structure of this diamond chain model. So if one could consider a diamond chain in which the atoms occupy just the ground state of each of the sides, there is only one coupling, there are no complex phases, and thus the band structure looks like this for all independently of the separation between the traps. There is no energy gap, and there is nothing you can do to try to modify this energy spectrum. But on the other hand, if one considers the model with L = 1 orbital angular momentum states that I have just introduced, there are two different couplings, and instead of just 3 states per unit cell, since there is the orbital angular momentum degree of freedom, there are 6 states per unit cell, and we obtain 6 energy bands that come in degenerate pairs. So in this case, there is a gap opening, and the 3 bands become flat in the limit in which the 2 couplings are equal. But there are always 2 bands that are flat. So this is for the band structure. if one just introduces the Hamiltonian in a computer and performs exact diagonalization, we obtain this spectrum in which we confirm that all the energies appear in degenerate pairs. And by performing exact diagonalization, we can look at the shape of the states, and we observe two particularly interesting families of states. So the first one is the flat band states, the states with zero energy, in which one realizes that the central sides of the ribbon have no population. And then there are these four peculiar states that appear inside the gap, inside the energy gaps, which I would like to show by performing some mappings that are topological, and also I would like to explain using these mappings why they lie on the right edge of the chain. Okay, so if we just analyze the model without performing any mappings, we have the difficulty that the energies appear in degenerate pairs, and thus, for example, it is difficult to compute topological invariance. But if we move on to this rotated basis frame, the diamond chain with two states per side gets immediately decoupled into two diamond chains with only one state per side. And in this diamond chain, since one of the couplings is negative, we can think that there is a net flux crossing each of the plaquettes. So the fact that we have obtained two decoupled exactly equal diamond chains explains the degeneracy that we observe initially in the model, taking into account two states per side. And also, the net pi flux that there is through each of the plaquettes can be related to the opening of the band gaps that was already discussed in a general framework for the diamond chain model. Okay, so by performing even a second basis rotation, we can map each of these two diamond chains into a modified SSH model in which from the horizontal couplings, this one here, is much stronger than this one. This one goes as the difference between the couplings involving and not involving exchange of orbital angular momentum. So in the limit in which the two couplings are equal, we see that we have these edge states, these states lying at the edge, and also we can easily explain the zero energy bulk states. I don't have time to explain it, but if one performs a third mapping, the Zaks phase, which is the topological invariant in 1D, can be computed. It can be shown that these states are topological, and also in the general case in which the two couplings are different, one can compute analytical expression for these zero energy states that are in the bulk. So the other limit in which I would like to discuss the system is the strongly interacting limit at unit filling, in which at zero order we see that there is a degeneracy of 2 to the n states due to the fact that each of the atoms that occupies one of the sides can be in the plus or minus state of orbital angular momentum. And thus it is very intuitive to perform a mapping in which the plus state is mapped into a spin up and the minus state is mapped into a spin down, and this spin chain will be mediated by second order interactions. Let me mention that there is a closely related work performed in Stockholm a few years ago in which they did a very similar analysis for bosons in the p-band of a two-dimensional optical lattice. So the second order processes that are relevant here are basically taking one spin in an intermediate state to a neighboring site and then back to the same site. So here I'm showing second order processes in which just one spin is flipped and it has a certain amplitude. But this spin flipping can also take place by interaction with the next central site. So if one computes these two amplitudes, one realizes that because of the minus sign that is due to the presence of orbital angular momentum, these two amplitudes exactly cancel. And finally, if one computes all the amplitudes of this model, one sees that because of destructive interference, it's not possible to flip just one spin. Whereas if one computes the amplitudes of of two simultaneous interactions between two spins, one realizes that in these cases there are always two processes involving angular momentum, thus the phases cancel, and the nearest neighbor interaction terms involving interaction between two spins always have the same amplitude independently of the direction of the interaction. So finally, the effective Hamiltonian has the form of an XYZ Heisenberg model in which the parameters that control the strength of the XX, YY, and ZZ interactions can be tuned by tuning the difference between the coupling strength of the original model. We have benchmarked this effective model by simulating spin dynamics and comparing them in a small system with the full integration of the Hubbard model, and we see that there is very good agreement even for two oscillation times. And also, since I mentioned in the first part of my talk, since the relative values of the coupling strength depend on the relative distance between the traps, by varying them, we are able to explore this line in the phase diagram of the XYZ model, in which it is particularly interesting the fact that we cross the critical paramagnetic chain in which the X and Z couplings are equal. So in principle, this proposal could allow to use a quantum simulator of the XYZ model to explore a phase transition. So these are the conclusions. I hope that I have shown that ultracold atoms carrying orbital angular momentum are a versatile tool to obtain complex couplings and perform various simulation tasks. And I have shown that this can lead to interesting physics in two limits. The first one, the single particle limit in which there is a gap opening, and in the strongly interacting limit in the Mott insulator, we can simulate the XYZ model of magnetism. And with this, I would like to thank you for your attention and to welcome you all to the ICAT conference that will take place in Barcelona in July. Thank you very much.
Thank you very much. So there's a couple of minutes for questions before going for lunch.
So I didn't understand, these flat bands are related to what people call the iron bone cages, or localized on a diamond?
Yes,
Flat?
so
These
yeah,
are
so
the same.
if one goes to this mapping, these states that belong to the flat band are always on the bulk of the chain, and they are very localized. So in this case, they would be localized, I think, along only 8 sites, but in the general case, they don't delocalize along the chain. They are concentrated. So yeah, it's related to that.
There's another question.
Thank you for a nice talk. I'm wondering if you have explored the flat band physics in connection to the strongly interacting limits of the spin chain problem.
Not yet. We have not explored that yet.
Are there more questions? I have a question myself, actually. So how do you avoid scattering into the zero orbital angular momentum states?
So this is a good question. You mean in the strongly interacting limit, I guess?
Yeah.
So in that limit, yeah. So if one computes the collisional amplitudes, one sees that it is not favorable to change the angular momentum. So basically, the transitions in which the angular momentum is changed are suppressed. So the angular momentum has to be conserved, and in the virtual processes in which two atoms would be in the same site, so for example, if you have two states in the L equal 1 angular momentum states, you wouldn't have the transition to the L equal 2 and 0. So, yeah.
Okay, so let's thank the speaker and all the speakers of the session. Thank you very much.